Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Good afternoon. So some folks at UW already heard this, but we were envious, so we asked Ander to also tell us about random games.
Okay, thank you. Hello, everyone. So, random games. So, I want to imagine two players compete in a game of skill. So, how might you model this mathematically? So you have a graph, a directed graph of positions. So the vertices of the graph are positions of the game, and the edges represent moves. And you have two players. So maybe you start at this position, and then Alice moves first. And these are all the positions that she could move to on her first move, the ones that you can get to. And then it's Bob's turn. So he has a move, and then Alice has a move, and so on. So I'm going to assume that Alice and Bob take turns. They alternate moves. And there's not really much loss of generality here because, for instance, if you had some strange game where Alice has 3 moves and then Bob has 1, then you could think of Alice's 3 moves as just 1. It would just be a different graph. However, I'm certainly not going to be considering simultaneous moves. So game theory, Nash equilibria type stuff, I'm not going in that direction. It's just taking turns. And right, so well, how does the game end? Well, I'm just going to say some terminal positions, which are simply vertices that have out degree 0, are designated wins for Alice or wins for Bob. Okay, so maybe this node is a win for Alice, this position is a win for Bob. Okay, so it's very, very simple. And if you want to, you might want to assume, and again, there's not really any loss of generality in any of these things, you could assume that the graph is directed acyclic, meaning it doesn't have any directed cycles where you come back to, you can come back to the same position, because if you did have a game like that, you could always just declare it to be a different position when you come back to it the second time and the third time and so on, if you wanted to. It would be a different graph again. And if you want to, you can label a position by whose move it is next as well. That can be part of the position. And also, if you want to, you can assume that the graph is a tree, because if you had 2 possible ways that you could come into the same position, then again, you could just call it a different position depending on how you got there. If you want to, you can assume it's a tree. I mean, I won't always assume these things, but you can assume that if you want to. Finally, and this is kind of important to just note, if you want to, you can assume that the way you decide whether it's a win or a loss is by what's called the normal play rule in combinatorial game theory. So the rule is simply if you have no possible moves when it's your turn, then you lose, and the other player wins. Okay, so and why is this without loss of generality? Because if you had a game that wasn't like that, then again you could just always modify the graph. I mean, if it's Alice's turn, but I guess I haven't got a good example. If it's Alice's turn, but it's a win for Alice, then you just give 1 extra move for Alice to make, and then Bob loses. So there's no real loss of generality. So I'll assume this most of the time. It's kind of convenient. Okay, so I want to think about optimal play. So that means just the players are very, very clever. So a strategy for Alice, say, is simply a map that assigns a legal move to every position that she might find herself in. Just a rule book for how to play the game. So you imagine Alice uses one strategy and Bob uses another, and you call Alice's strategy a winning strategy if it guarantees that Alice will win no matter what strategy Bob uses. And it's pretty easy to see that if you have a finite directed acyclic graph, then exactly one player does have a winning strategy. I mean, the game has to end, and so someone has to win. It may be difficult in particular cases to decide who does win, of course. But on an infinite graph, there's a third possibility, and sort of by far the most interesting possibility, at least in the sort of directions I'm going to be discussing, which is that it's a draw, which is that neither player can force a win. Neither player has a winning strategy. So a very stupid, simple example, if the game graph is simply a directed path off to the right, then the game never ends. You just keep on moving to the right. So that's a draw. And throughout, I'm going to assume that the players know the entire graph and they're infinitely skilled. So I'm not going to consider computational questions of how hard is it to decide on your strategy, although those might be interesting as well. So, okay, you can do some pretty easy things. You can classify positions, vertices of the graph, as n positions, which means a position from which the next player wins, next player to move, the first player, or p position for which the previous player, i.e. the player who just moved or the second player, has a winning strategy or draws. So this is the outcome of the game with optimal play. And it's not very difficult to convince yourself that there's a sort of a recurrence for trying to compute these things. If this is a node and these are all the nodes that you can get to from it, and you know the outcomes of them, then you can compute the outcome at this one. So for instance, if you can get to a p position from here, then that's an excellent move to make, because that means you're leaving your opponent in a position where they will lose. So that's a very good move. So that means this is a winning position. This is an n position. And if all the things you can get to are n positions, then too bad for you, you're going to lose. So that's a p position. And then when you involve draws, if there are no p's, but there is at least one d, then this is a d. It's not too difficult. But note already that this recurrence in itself is not sufficient to determine game outcomes, because consider this stupid example where the game graph is just an infinite line, then every vertex d is a solution to that recurrence, and it's the correct one, that really every vertex is a draw. But these two, alternating Pn or Np, are both solutions to the recurrence. So on an infinite graph, you need to know some more, and note, if you were to cut this path off at some point, then either this or this will be the truth, depending on where you cut it off at an even or an odd distance. So saying that it's a draw is something to do with saying if you cut the graph off a long way away, it depends how you do it, what happens at the beginning. Okay, so again, I'm assuming everything is known to both players and there's no randomness at all. You just have a deterministic graph and you play deterministically. So, okay, what are interesting games to look at? Well, there's kind of a bit of a tricky question here, because on the one hand you have some simple mathematically idealized games where there's some interesting theory of them, but they're not really the kind of games people play in practice. And on the other hand, you have games like chess and Go, where people are very interested in them in practice, and there are definitely interesting computational questions, like how do you make a computer play Go? But theorems about chess and Go, you don't expect there to be many interesting ones because they're just too specific. So what is a good thing to ask? Well, here is one perhaps interesting middle ground you could try. You could ask, what happens in a typical game? What does a typical game look like? So that's what I'm going to focus on. So I'm going to choose the game itself at random. So there's still not going to be any randomness in the game play. It's just I bring in two players and I tell them, here's a game I cooked up for you to play. Why don't you play it? And I chose it at random. Okay? So that's what I'm going to do. And I'm going to talk about three examples. So again, remember, with the way I'm doing it, a game is just a directed graph. So I just want to think about some interesting models of directed graphs. I'm going to talk about three cases. All these are joint work with James Martin, who's now here for a few months. Very happy to have him here. And depending on which one, it's also joint with Irene Marcovici and Riddhipratim Basu and Johan Wastlund. So I'll consider Galton-Watson trees, and I'll consider directed percolation clusters, and I'll consider undirected percolation clusters. And bear in mind the way I described it, it was a directed graph, so I haven't told you what it means to play this game on an undirected percolation cluster, but I'll come back to that and I'll give a sensible definition. And well, you know, this isn't going to be one of those talks where I just try to impress you with how clever we are at having solved all the problems. It's not going to be like that. It's just I'm trying to open the door to some interesting circles of questions. We managed to prove some things, but there's a lot more to do. We've just kind of scratched the surface. And it's already interesting that in trying to answer essentially the same question in these three settings, we ran into just all sorts of interesting old friends from the world of probability theory: continuous and discontinuous phase transitions, probabilistic cellular automata, hardcore models, bootstrap percolation, and maximum matching. All from considering the same question, essentially.
It's completely at random, have to be all the topics you have in
Yes.
your work with.
Somehow, I don't know which way around the causality goes. Yeah. And there'll kind of be an increasing difficulty gradient as we go down. So here, really all the proofs, or most of the proofs, are kind of exercises, although the results are quite interesting and striking, and you know, give you some clues about what you should be asking lower down. And here, it's just on the cusp where somehow magically the theory is just strong enough to be able to prove some interesting things, but it's sort of very fragile. If anything broke, it would be much harder. And down here, by far the most interesting questions are completely open. We have no idea how to attack them. I think they're very, very interesting, and we managed to find some consolation prizes, some things we could prove. But the main question is open. All right, so let's get started with Galton-Watson trees. So let's suppose that the graph, this directed graph that I choose to play my game on, is a Galton-Watson branching process with a non-deterministic offspring distribution. So you just have one vertex at the top, and that has a random number of children, and each of those has a random number of children, and so on, all with this same distribution. And I'm going to play the normal game on this graph. So you start at the top, you take turns to play, and if you find you are at a vertex with 0 offspring, then you lose, and the other player wins. Okay? So of course, if mu has mean less than or equal to 1, then the branching process dies out. So the tree is finite, and that means certainly there are no draws. Right? Draws can only happen on an infinite graph. But if it has mean greater than 1, then the tree is infinite. So you can ask, can there be a draw? Right? So you have an infinite random tree, and so draws can take place, but do they happen with optimal play? So maybe there is this infinite path, but somehow it's not thick enough for. So to have a draw, you somehow have to have a thick path, not really a path, a cluster, so that neither player can force the other one off it and cause a win. Right? So it's a question.
You're assuming P0 is positive.
That's right, yes. So you better assume P0 is positive, otherwise it's all draws. Okay, so not so surprisingly, if you've thought about questions like this, one can do really an exact analysis on a Galton-Watson tree. So first of all, and this is true much more generally, there's a sort of a compactness argument that says if Alice can win, say, then she can guarantee to do so within some finite number of moves, and that number depends on the tree, so it's random. Right, so somehow wins are local in some sense, and therefore the sensible thing to do is truncate the tree at level n and declare all the vertices at level n to be draws. So you just play the game on this top finite piece, but with different rules. You say, if the game ever gets to the bottom, we call it a draw, and then you see what happens. Okay, so you can just apply the recursion upwards to figure out what all these other vertices are and figure out what the root is. And because of this thing, it's pretty easy to see that the probability that the root is an n position when you truncate converges to the probability it's an n position in the infinite tree. And similarly for p, and therefore it's true for d as well, because that's 1 minus the other 2. Right, so, and on the other hand, you can compute all these things using generating functions. If you take the generating function of the offspring distribution, then you can just translate this recursion into a recursion involving that. If you know n, you can compute pn plus 1, etc. So the upshot of all this is you look at 1 minus the generating function of the offspring distribution, and it's all about the fixed points of that. So d, the probability that the root is a draw, that the game is a draw with optimal play starting from the root, is the difference between the biggest fixed point and the smallest fixed point of not f, but the iterate f of f in the interval 0, 1. Turns out, easy computations, and n and p are given in terms of that as well. So there are draws if and only if this function, the iterate f of x, has multiple fixed points in the interval. So here's an example. Just the simplest example is binary branching. Your offspring distribution is you have 2 offspring with probability p and 0 offspring otherwise. Okay, so of course, we know what the mean of this is. So the tree is infinite if and only if p is greater than a half. So here's what happens with the game. Here's p along the bottom. We're increasing this p, which is the probability of having 2 offspring, and in any vertical line, the width of the red part is the probability of an n position, the width of the blue part is the probability of a p position, and the width of the green part is the probability of a draw. So up to root 3 over 2, which you'll notice is not equal to a half. So again, the phase transition for the tree to be infinite is at p equals a half. But you don't have any draws until you get to p equals root 3 over 2, and then you start having draws with positive probability, and the probability is the width of this green bit, so it's a continuous phase transition. So right at the critical point, it's still 0, and then it grows. So that's what happens. All these curves are computable in this simple example. So basically what's going on is you have this f of x, and you're interested in fixed points, so you'd better subtract x from it. And below the critical point, it's just some nice curve with a root somewhere. And then as you cross the critical point, it starts to have a point of inflection here. And after the critical point, it has 3 fixed points, and the outer 2 move apart. And the distance between them is d. Okay, so you can do lots of nice examples. You could look at a binomial distribution, which is percolation on a regular tree, and you have a similar picture as p varies, basically. If you have a continuous phase transition where you start having draws not at the critical point for percolation, but strictly higher. And with a Poisson distribution, turns out similar. The critical point is at lambda equals e for draws. And interestingly, with a geometric distribution, you never have any draws, no matter what the parameter. And once you understand this picture with fixed points, you can concoct weird examples. So there are examples where you vary the offspring distribution continuously, but d has a discontinuous jump from 0 to positive. And you can even, if you concoct it sufficiently, you can even make it jump from one positive value to a different positive value. And you do this just by figuring out what you want this curve to do to make the fixed points behave strangely. So, okay, I mean, sort of the short answer is anything is possible if you concoct a strange distribution. So, okay, a couple of other things you can do. This was the normal game, which is where you lose if you cannot move. There's also what's called the misère game, where you just change the rules for winning. You say, if you cannot move, you win. And then there's also this sort of intermediate one, which we call the escape game, where you have one player called the stopper who is trying to make the game end with someone not able to move, and the escaper is trying to make it continue forever. So you can do similar things with these. For the misère game, things come out similarly to the normal one. For the escape game, it's actually different. For the escape game, it seems that discontinuous phase transitions are the norm, from no probability of the escaper winning to suddenly jumping to positive probability. So again, for binary branching, the picture ends up looking like this. You have one fixed point, and then at some point this curve dips below the axis, and you suddenly have a fixed point much further to the left. You have a jump. You can compute it in this example. But again, you can concoct examples with continuous transitions, it turns out, so it's not as nice as you might think. However, we wanted to sort of salvage some rigorous statements that are true in general. So for the normal game, P and N are lower semi-continuous functions of the offspring distribution. So basically, the only way you can get jumps is by D-jumping. And similarly for the other games. And for mu, where the support is too small, all these probabilities are continuous. And finally, here's something that says for the escape game, which is the one where sort of discontinuous phase transitions are the norm, there's this special way that the escaper can win, which James actually mentioned in the lunch yesterday. If the mean times the probability of having one offspring is positive, then the escaper can just keep letting the other player have no choice at all. So that's a sort of very special way to escape. And the places where the escaper wins, is this what I meant? Yeah, the set of distributions where the escaper wins contains the set where this is greater than 1, and it's a closed subset of the set where it's less than 1. So it's not quite saying that this is a closed set. If I could say this was a closed set, that would mean you only get discontinuous phase transitions. And it's not as strong as that, but sort of the only way you can get a continuous phase transition is by sort of carefully going across this boundary. So that's what we have. So how about some inequalities? You can compare these three games. And we have 10 inequalities between like the probability the next player wins in the normal game and the misère game. The twiddle means misère game. And they sort of come into three categories. These ones just hold point-wise for any directed acyclic graph. They come from arguments like if you can win in the normal game, then you can win as the stopper, because that's just an easier thing to do. It's an easier task. And then there are these ones that are sort of a little bit more subtle. They use strategy stealing arguments. They say that because it's a Galton-Watson tree, after one move, you're sort of still in the same situation in distribution. And then these are kind of interesting. They're not super hard to prove, but we don't really have intuitive explanations for them. So maybe the most interesting is that draws are more likely in the misère game, weakly more likely in the misère game than the normal game. So if anyone has any intuition why that would be true, that would be kind of interesting. Kind of interested. And no other inequalities are true in general. Okay, so that's trees. So let's talk about another random graph. So let's do site percolation on the directed square lattice. So you have Z2, the square lattice, and make it directed. So every edge is directed to the east or to the north. And we do site percolation on it. So each site is closed independently with some probability P. So I'm just deleting some vertices at random. And I play the normal game on the open subgraph, the vertices that remain. So you're not allowed to move to a closed site. So again, so for some reason our P is 1 minus the usual P of percolation for whatever historical accident. So if P is big, there are lots of closed sites, then the set of vertices you can get to, so this should be the PC for directed site percolation, I didn't even say that, then the set of vertices you can get to is finite, so definitely there are no doors, but if not, then the graph is infinite, so maybe there could be draws. So again, we can ask whether there are. So here is the picture. So here's a simulation. So p equals 0.2, so 20% of vertices are closed or deleted. And again, what you want to do is, consider diagonals, right? If you know the outcome of the game on a diagonal like this, then you can compute what happens on the next diagonal down. So the thing you want to do is put draws on the boundary. So here's what happens if you declare the game a draw when you get to this boundary and then propagate backwards. So red denotes draw positions, and blue and green are wins and losses. So you can see, well, the sort of draws certainly persist down quite a long way, and if you want to know what happens on the infinite lattice, then that's equivalent to asking, what happens if you just propagate further and further down? Do you ever see any red surviving? And you ask that question for each p, of course. So this is p equals 0.2, and this is p equals 0.1, so here it seems pretty clear that the draws die out. And then maybe if you go back to this, you sort of see that the red doesn't seem to grow very often, and then it gradually seems to get eaten away, so perhaps it always gets eaten away. But the question is there any p for which the red survives? Okay, well, here's a way of looking at that question. So you can regard, if you want to, you can change the rules of the game. You can say, rather than it being forbidden to move to a closed site, you can say, if you move to a closed site, then you immediately lose. So that's equivalent, because no one will ever want to do it, so it's the same game. So it's just convenient to regard closed sites as end positions. And again, we can imagine turning the lattice this way around. So if you know the game outcomes on one diagonal, then you can compute the next diagonal down. And one way to look at it is there's a probabilistic cellular automaton. So if you know the two states above you, then there's just some rule for computing the one below, and sometimes you have to toss a coin. Okay? So here's a lemma, which I'm not going to prove. So draws occur if and only if this probabilistic cellular automaton has multiple stationary distributions. The stationary distribution means you have some distribution on the configuration of a diagonal, and then you propagate it one down, and it still has the same law. Okay? Furthermore, that's also equivalent to it has multiple stationary distributions without d's. So if you just consider you don't have any d's, you just have p's and n's, and you just use this rule, that gives you a simpler cellular automaton with just two states, and it's equivalent to that having no draws. And I'm not going to prove this, but you should think of it as being a bit like these pictures we started with, where if one player has a win in the game, then they can win locally. It's not a global property, it's a local property. So if there are no draws, then there ought to be just one stationary distribution. And on the other hand, if there are draws, then it's somehow telling you that there are, even with just p's and n's, there are multiple solutions, like in that picture at the beginning with z alternating n's and p's. So if you can have draws, it's telling you that there are multiple possibilities. So in any case, this is true and not too difficult to prove. So we want to know, does this have multiple stationary distributions? Now, this brings us to some difficult territory. It's widely believed that all simple one-dimensional probabilistic cellular automata with positive rates have unique stationary distributions. What does positive rates mean? It means you have some rule like this, some cellular automaton rule, and you no matter what symbols you see above you, you always have positive probability of producing any other symbol below you. And this isn't actually true here, because here you definitely produce an n, for example. But it's kind of almost true in the sense that if you, for instance, if you take 2 steps, then locally you could produce anything. So, I mean, morally, not just morally, this cellular automaton is certainly in the category where it's widely agreed that you would expect it to have a unique stationary distribution. However, it's, I mean, although this is widely believed, it's proved only in some very specific cases, and it's hard to prove it in many cases, and it requires different techniques in different cases. So it's potentially a hard thing to prove. And related to this, I mean, well, what does simple mean? Of course, there's no specific meaning, but there's an extremely, back up. It was, for a long time, believed that you can remove the word simple, so that any one-dimensional probabilistic cellular automaton with this positive rates condition has a unique stationary distribution. So it's widely believed. It's called the positive rates conjecture. But then Gatch in 2001 gave an extremely complicated example, counterexample to that. However, it's an exceptionally difficult 200-page proof, and I think it's fair to say that no one other than the author really understands it, and you know, maybe not universally accepted to be correct, but
definitely not universally accepted.
There you go. You have a counterexample in the order. But in any case, this is extremely complicated, and the construction is extremely complicated. So one certainly doesn't expect multiple stationary distributions for a nice, simple rule like this. It would be extraordinarily surprising. Okay, so we expect unique stationary distribution, therefore no draws. So can we prove it? Well, here's a very interesting picture. So consider just 2 successive diagonals, and let's just look at the picture where there are no Ds. We just have Ps and Ns. So you have some configuration, and of course you can compute the configuration on the next line. And actually the rule is if you can see a P above you, then you're an N, and if you see 2 Ns, then you toss a coin. That's a summary of what I said before. So now, well, you could imagine keeping going. Of course, you compute the next diagonal. And, well, to save space, I could actually write the next diagonal above instead. I could write it up here, because this is the same shaped zigzag path. And again, the rule is if I see 2, what was it again? If I see 2 P's, I write an N, and otherwise I toss a coin, and I compute the diagonal above. And I could keep going like this. Now, here's something else that you could do on Z. Look at the hardcore lattice gas, which is a standard statistical physics model. The hardcore model is a distribution on configurations of zeros and ones on the vertices of a graph with no adjacent ones allowed and weighted by some parameter to the power of the number of ones. At least that's how you do it on a finite graph, and then if you wanted to do it on an infinite graph, there are ways of taking limits. And there's a Glauber dynamics which is for which this measure is a stationary distribution, which is you choose a vertex to update, and then when you update a vertex, if any of its neighbors is 1, then it has to be a 0 because you're not allowed to have 2 adjacent ones. And if all the neighbors are zeros, then you toss a coin with some appropriate probabilities that depend on this parameter lambda. Okay, and well, if you think about the hardcore model on Z, one thing you can do is apply Glauber dynamics alternately on the odd and even vertices of it. The hardcore measure will be stationary under that dynamics. So you have Z, and I draw it in this zigzag fashion, and you alternately apply that rule on all the odd sites simultaneously and all the even sites simultaneously. And of course, that's the same thing as the picture I just showed you with N is 0 and P is some function of lambda and so on. So because of this correspondence, it's a fact that Gibbs distributions for the hardcore model on the line are in bijective correspondence with reversible stationary distributions for the probabilistic cellular automaton with no Ds. And it's reversible, well, yeah. It is reversible because this picture is reversible. I won't go into the proof of the theorem, but one can prove that. And, well, it's rather well known and not surprising that the hardcore model on Z, because it's a one-dimensional graph, has a unique Gibbs distribution. So that means that my PCA has a unique reversible stationary distribution. But of course, that's not enough for what I wanted. That's not enough to prove no draws, because maybe there are some other non-reversible stationary distributions. So unfortunately, that doesn't help. However, using different methods, kind of new methods, we did manage to prove what we wanted. So on the square lattice, no matter what P, there's a unique stationary distribution and there are no draws. And moreover, if you're interested in the game, you can even compute the probability that the origin is an n position and it's some function of P. And just to sort of show how fragile all this is, so how did we prove this? First of all, we proved it by a very different method, by assigning a rather subtle weight function to configurations and proving that that weight function is monotone. And it's not so obvious how to come up with that weight function. And just to show sort of how fragile this is, there's another game called the target game where you win if you ever move to a closed site, for which we can still prove that there are no draws, but we cannot compute the probability of a first player win like this, and it's really a fundamental obstacle. It's not just we didn't work hard enough. And also for the Misère version of the game, it's unknown whether draws occur. Somehow this correspondence, well, this technique doesn't seem to work. So why did I bother telling you all that business about the hardcore model if it's no use? Well, okay, you can try to use it in the other direction, in other settings. So we can still try to use it in the other direction. If there are multiple hardcore Gibbs measures, then you have draws. And one place you could try to use that is in higher dimensions. So here's a case where it works. So take a d-dimensional lattice, so not ZD, but the even sublattice of ZD, the vertices whose coordinates have even sum. And consider the game where you're allowed to move. You have to move up in the vertical direction, and you can move in one other coordinate any way you want. Okay. That's a graph, a directed graph. And this corresponds to a hardcore model on ZD minus 1, one dimension lower, by a similar correspondence to the one I showed you. And this, the hardcore model, is known to have multiple Gibbs measures in dimensions 2 or more, this d minus 1 being the 2 or more. And so that means in dimensions 3 or more, this game does have draws. I mean, for p sufficiently small, the probability of a draw is positive. And, well, you might ask, what about the usual lattice, ZD, if I want to consider 3 dimensions, that maybe the most natural directed graph is just ZD, and you're allowed to move north, east, or up. You're allowed to increase any coordinate by 1. That's the directed graph. Those are the allowed moves. Well, here, this hardcore correspondence really breaks down. And again, it's not just because we were too lazy. There's a fundamental problem. So basically, the kind of thing you would want to do is, if you're on Z3, you could consider 3 successive layers of Z3 and sort of imagine how they connect to each other, and you get a triangular lattice. But then what you want to do is there are these 3 classes of vertices that they naturally fall into, and you want to consider hardcore dynamics where you update each of these sets of vertices in turn, but for example, you update the green vertices just conditional on the blue vertices. And that's no good because they're adjacent to the red vertices as well. So that's just not the hardcore model. It's some other dynamic. So it really doesn't work there, but we conjecture nevertheless that again, in 2 dimensions you do not have draws, that's a theorem, and in 3 dimensions we conjecture that you do, for p sufficiently small. All right, so finally, third example. And as I say, this is in some ways the most interesting, but also the hardest. So let's consider an undirected lattice. And again, I'll make it random by making each site of the lattice independently closed with probability p. Toss a coin for every vertex and make it closed. So somehow the normal game is very boring on an undirected graph. The normal game being there's a single token on some vertex, and when it's your turn to move, you can move it along an edge, and you lose if you can't move. So most of the time, no one's going to lose. So for instance, anyone who feels they're in a losing position can just, I don't know why I drew a cycle like this, you could even just make the token shuttle backwards and forwards between two adjacent vertices if you fear you're going to lose. So it's not a very interesting game. Here's a way we could make it more interesting. There's a game that we call Trap. Alice and Bob take turns to move a single token. There's a single token located on some vertex, and you move it along an edge. And you're allowed to move it to any open site, provided that site has never been visited before. Okay? And you're not allowed to move it to a closed site. And again, if you can't move, you lose. Okay, so it's kind of a fun game. You're trying to trap your opponent by trapping them in the path where you've been already, but using the closed sites as well. So this is an interesting game. And since we're concentrating on ZD, and since ZD is bipartite, I'm going to rename the players. There's one player who always moves to even sites, and I'll call that player Eve and the other one Odin. So here are some simulations. So here is, of course, not Z2, but a square. And as before, the good thing to do is declare the boundary to be a draw. Okay, so we play the game on a square board, but if the token ever gets outside the boundary, we just call it a draw. Okay, so the sites that are outlined in black are closed, and white places starting vertices for which the game is a draw with optimal play, and red is Odin wins, blue is Eve wins. Okay, so you see some very interesting things. If there are not many closed sites, then basically it's all draws. Not very surprising, because the closed sites aren't enough for anyone to trap the other person. You increase P a little bit, and there are some little regions where maybe Odin can force a win locally, but globally it's mostly draws. And then P gets a little bit bigger, and suddenly there's a huge region where, as it happens, Eve can force a win anywhere in here. And there are these interesting checkerboard regions as well that are half blue and half white, and here's a little region that favors Odin. And then you make P a little bit bigger, and there are sort of more of these regions and smaller regions somehow. So that's a square of size 50, I think. Here's a bigger square of size 200. And again, so there's a big difference here, which is that the P equals 0.1 picture, here it was mostly draws, and here it's not. So here, if you take a bigger square, suddenly there are these regions where one or other player can win again, but they're very big, and it seems like somehow you need this whole region, and the previous square wasn't small enough to contain it. So the picture I have in mind by looking at these simulations is the following, that for each P, there is some typical size of a region within which one player can force a win. And this size diverges as P gets smaller, and if your square isn't big enough to contain one of these regions, then it's mostly draws. That's sort of the picture it seems to be showing, because here they're big regions, and then they get more grainy when P gets bigger. And furthermore, it kind of appears that, at least perhaps, if you take the square big enough, even with, whoa, what happened? If you take the square big enough, maybe even with P equals 0.05, someone wins, and you don't get so many draws. So it's hard to tell, but you might guess that the critical probability is 0, so that when you take the whole infinite lattice, Z2, you don't have any draws. And again, I know there's a lot more you can say looking at the pictures. It sort of seems that these red and blue regions kind of abut each other, so there's no corridors of draws in between. And again, you have these interesting checkerboard regions. You probably can't see it, but that's checkerboarded red and blue for a while. So the first player wins from this region. So very, very interesting. We can't prove any of that. But as I said, a reasonable conjecture is that on Z2, maybe for all P, you have no draws. And again, we don't really have much to back this up. But if I had to guess, I would say in 3 or more dimensions, you have a phase transition. And we've lost the screen again. In 3 or more dimensions, if I had to guess, I would say perhaps you do have a phase transition. You do have draws for P small enough. Okay, we can't prove any of that. So we backed off to see if there was something we could prove. Yeah.
So you don't think it's like bootstrap percolation where PC would be 0 for all dimensions?
Right. I mean, I just don't know, but by analogy with the directed case, I would say.
Directed case you can reduce one dimension.
Yeah, I just don't know. But yeah, I think these are very, very interesting questions and probably very hard. Okay, so how can we save face and prove something? So because the graph is bipartite on ZD is bipartite, you can give one player a big advantage. So you can say you have odd and even sites of ZD, and I could assign different probabilities to them, different probabilities of being closed. And the extreme case is odd vertices are closed with some probability P, and even vertices aren't closed at all. All even vertices are open. So this gives a massive advantage to Eve, because Eve moves 2 even vertices, and she never has a problem. They're all open. So it definitely gives Eve an advantage, but you can ask how big is it? Try to make that quantitative. So here's kind of how this game tends to go. So suppose Odin moves to this site. If we can get it back. So then, well, Eve's going to just move there. And then she's won immediately, because Odin has no moves. So that means, really, that site there is effectively closed. It's forbidden to Odin. If he ever moves there, he's dead. And Yuval sees where this is going. So now you can iterate this argument. So anytime you have a site, every time you have 3 sites that are closed or even effectively closed like this, you can make the 4th one effectively closed. So that means that one is effectively closed as well, and therefore that one, and so on and so on. So this model is it's on a rotated version of the lattice. It's a variant of bootstrap percolation called modified bootstrap percolation. So the model being whenever you see 3 sites in a configuration like that, you add the 4th one in the square. And a standard but rather surprising result on this is that on Z2, for every P, all the sites end up blue. If you start with random sites, no matter how small P is, they all end up blue. So you can deduce from this that Eve wins from every initial vertex. And this extends to various d-dimensional lattices. It could likely be extended to ZD, but it's a little bit harder because the lattice is not really the standard one. Could probably be done. So okay, let's try to make it a bit more interesting again. So this made it too easy for Eve. Let's give Odin some advantage back again. So let's play it on a finite board. Let's play it on a finite square, and we will choose the parity of the square itself so that we give the boundary to Odin. So we just choose the parity of the square so that the external boundary vertices are ones that Odin moves to. So like if Odin moves to here, he's 1. So basically Eve tries to win by using the closed vertices, and Odin tries to win by forcing Eve to the boundary. That's roughly what happens. So you can play around with this model. So let's play it on a size n diamond. So now we have two parameters. We have n, the size of the square, and we have p, the density of closed sites. And this bootstrap argument tells you that, bootstrap percolation gives you bounds involving finite squares. So it tells you that Eve wins with high probability if n is big enough compared with p, if it's bigger than exponential of constant over p, which is pretty big, of course. But that's not tight. The bootstrap argument is not tight for the game. So here is a place where Eve can win, even though this argument from 2 slides ago doesn't tell you that, this argument of effectively closed sites. So you can work it out in this example. Maybe I won't do it right now, but certainly this vertex doesn't become occupied by the bootstrap model, but Eve wins starting from here. And here's one way to do it. So the correct scaling is actually not this exponential one that you get from bootstrap percolation, but it's n is approximately constant over p. So more precisely, we know that if you do this on a diamond of size n with p, then so if n is large compared with 1 over p, then Eve wins almost everywhere. Excuse me. Well, it comes up on the screen here. Haven't got long to go anyway. Right, if n is big with respect to 1 over p, then Eve wins. If n is small, then Odin wins. And it's not quite for every site, but it's for most of them. And there are some logs that we couldn't get rid of, so it's not quite a tight result. And you can deduce things about what happens if you have odd sites closed with probability p and even sites with probability q as well. Not very tight results. So where all this comes from is there's a little bit of magic. This game of trap on any graph, actually, is related to maximum cardinality matching. So here's a fact. On any finite connected graph, the first player wins starting from a vertex v, if and only if v is included in every maximum matching of g. Maximum, not maximal. So it's all about maximum matchings, and this is easy enough to prove. It's just by induction, you say, if this is true, then you find a good first move, and if it's not, you find all first moves are bad. So there's another interpretation of all these questions, which is at least as interesting as the game one. They're questions about sensitivity of maximum matchings to boundary conditions. You take a big chunk of your graph, you cut it off somewhere, and you ask what maximum matchings look like in the middle near the origin. Does it depend exactly how you cut it off or not? So that's what draws are all about. So yeah, I guess I should wrap up. But the way we prove that theorem is by finding matchings and finding ways to modify them, etc. So there's a bunch of open questions. As I said, most interesting one, play trap on an undirected percolation cluster on Z2 or on Z3. Are there any draws? We don't know. The directed game on Z3, remember that there's this hardcore correspondence, but it doesn't work on Z3, so we don't know what happens. And yeah, so one thing I didn't talk about, really, you can ask whether you have phase transitions in any of these cases. So take, for instance, this 3-dimensional even lattice that I showed you towards the end. So 3-dimensional directed even lattice. So we know that you have draws if p is small enough and not if p is big enough, but we don't know whether the probability of a draw is monotone in p. So we don't know whether there's just a phase transition point. You can try to improve these bounds that we have up to a logarithm, or you can just ask what actually happens in here. And by the way, if you want to understand this first question, what happens on the undirected lattice, then it wasn't just a face-saving exercise that we looked on this finite diamond. You probably want to understand how the game works on finite regions first, because supposedly there are these red and blue regions that abut each other, so you'd better understand how they work. So what happens within this window, you could ask. Yeah, well, there are many, many questions. You can look at the target game. Can you compute the winning probability? That was back to Z, that was. And there are Mézières versions. There's non-bipartite graphs, etc., etc. So I'll stop that.
Any questions? Can you somehow incorporate random turn games into this?
Well, yeah, I was wondering about that. It seems as if it's a different question, because you don't know the randomness ahead of time. I mean, what we're doing is we're saying the randomness is all in the graph, and then you know it. So it seems like it's different, but maybe there's some possible synergy. Hi.
So in the east bounds, log 1 over
Yeah.
E, does it come from a probabilistic construction?
Yes. Yes.
So, when you state that
These ones, right?
yeah.
Yes. Yes.
I see. So on a technical level, those show up because there's a randomized construction, but you may expect that there's a better.
Yes, you might expect that. We really don't know. I mean, I wouldn't be surprised if you could improve one or other bound, but it's perfectly possible that there is a real interval in between as well, where something different happens, like Eve wins in certain places and Odin wins in other places. It's an interesting question, and I don't know. Yeah, I mean, there are pictures like this. We explicitly construct matchings. I mean, for the one bound, we explicitly construct good matchings, and then we somehow modify them along alternating paths so that we can produce different ones that correspond to different vertices. And there's probably some slack in our constructions, and then the other way, there's somehow we prove non-existence.
Modifiable to leave almost even side.
Almost. That wasn't right. No, almost every even side, probably. Yeah. So we find a very close even side. Yeah. Right. So basically, on this side of the bound, you want to prove that there's a matching that matches all odd sites, but leaves any particular even site that you're interested in unmatched. That's basically what you have to do. So we start by constructing one matching, and then we modify it along an alternating path to get the other ones we want. And then, this one is somehow the other way around. But yeah, I mean, behind these, there are, fairly concrete constructions, and it's perfectly possible one could improve them.
Is there no other questions? Thank Andrew again.